Welcome and hello. This is a video exercise using the FHWA hydraulic toolbox. This exercise I have titled Minimum Inlet Spacing Analysis. So what we're going to be doing is looking at the minimum spacing between inlets on a horizontal or completely flat roadway and answer this question. How is the minimum inlet spacing affected by the cross slope and by the allowable top drainage width? Cross slope and top drainage width are both input variables for the horizontal grade inlet calculator. That's this right here. So this is going to be the calculator we're using. I'm going to delete it real quick just so I can show you how it's loaded. Just like all the other calculators, you can right click on your project and then add horizontal grade analysis. So let's go ahead and open that up. We'll return to the data in just a moment. At the top is our input parameters, and then down below we'll have our results. So the result that we're most interested in is that maximum spacing between inlets. And let's go ahead and start with our data input. All right, so the rational runoff coefficient, C, is 0.9. In fact, I think that's the actual number, 0.9. Yep. It could be more, it could be less. I mean, zero point 0.9 is pretty high. 1 would be the maximum. But if the soil surface for this particular watershed was more pervious, this would be a lower number than 0.9. Next, we have our return period and our duration. The return period is 10 years. The duration is 5 minutes. And we have an IDF curve right here, which corresponds the intensity of the storm with the duration and the return period. So that intensity is what we want to put right here. We're in units of millimeters per hour. So if you haven't already switched your model over to metric units, go ahead and do that if you want to follow along. All right. So let's go ahead and get that intensity of the storm in millimeters per hour. I'm going to click back over here to the notes. And remember, return period of 10 years, duration of 5 minutes. Here's the IDF curve, and I've blown it up a little bit larger in the next slide. So the duration is across the bottom along the horizontal axis. The rainfall intensity is the vertical axis, and these individual lines represent storm events, different recurrence intervals. The next slide here, I've actually added labels so it's a little easier to see. Again, we have duration, rainfall intensity, and the return period. I've highlighted the two lines of interest that we were given, which is the 5-minute duration and the 10-year return period, this pink colored line and yellow colored line, respectively. So where those two lines intersect give us the point, and the vertical axis of that point represents the rainfall intensity. So that came out to about 3.5 inches per hour, which converts to about 89 millimeters per hour. This 89 millimeters per hour is what we want to use in our calculator right here. So let's just type in 89 millimeters per hour. All right, so I'm going to tab off. The next field down is the width of the roadway drainage to the curb. And then we were given that was 8.5 meters, 8.5. Next down is the cross slope of roadway drainage to curb. So this is one of the parameters that we're going to be changing. And then the other parameter we're going to be changing is right down here, allowable top width of drainage against curb. So let's return to those. And then Manning's roughness coefficient 0.015 is what we were given in the problem statement. Okay, so let's talk about cross slope and allowable top width. I'm going to bring up the given data here. So Manning's N 0.015. Now for the top width T, that's going to range from 1 to 3 meters. That's just the range that I'm interested in. And then the range of cross slopes of the road is 0 to 0.05. So is really let's go from 1%, so 0.01 up to 5%. 0 would give us no results. That's why the roadway would have a specific slope S sub x, as you see in this diagram from the front view. To give me a little direction as to how I want to attack the data, I've created a data worksheet in my Excel file, and I've got cross slope ranging from 1% up to 5%, and then the allowable top width of drainage from 1 meter up to 3 meters. This will give me 15 data points, and I think this would be enough to get a general idea to understand how the maximum inlet spacing is affected by these two different variables. Let's start with this cell right here, which is 1% cross slope and 1 meter allowable top width of drainage. I'm going to move that off to the side, get the calculator up onto the screen here, Actually, let me move that right there. Cross slope, we're going to go with 0.01. And then allowable top width is 1 meter. This is the most extreme case, which is why we have a maximum inlet spacing L sub C of 5.37 meters. So I'm going to type that in right here. That is absurdly small because of the data. So we won't be using that, but I wanted to sort of get some extremes to our data, hence the point of having a large range. All right, let's just go ahead and march across with all the 1% data first. So I'm going to change the top width to 2 meters, the results, 3 meters, get the results. And when I say results, I'm really just looking at the maximum inlet spacing, L sub C, the second row in the results here. All right, so changing the 1 meter to 2 meter, as soon as I tab off, it recalculates 23.19. So I'm going to come up to say in 23.19, and then the 3 meter results is 54.55. 54.55. Okay, so what we can tell already is that as the allowable top width of drainage increases from 1 meter to 2 to 3, then the maximum inlet spacing also increases. Let's go ahead and reset the maximum top width to 1 meter, but then change the cross slope to 2%. So 1 meter here and then 0.02. When I tab off, I get new results. We're looking at 14.57 meters. 57, okay. And then for the 2 meter top width, 62.91. 62.91. Finally, for 3 meters, that's 148.01. 148.01. Okay, so between 1% and 2%, we notice that the higher percent cross slope results in a larger maximum inlet spacing. Now I'm going to just go ahead and run the rest of these calculations on my own, and here they are. So let's move this over here. As you can see, the trends that we noticed initially continued on for the rest of the data. And then over on the right here, I have a plot that says that the maximum inlet spacing, which is the dependent variable on the vertical axis in units of meters, is shown for the 3 different top widths and for the 5 different percentage points that we chose for our road cross slope. So just to reiterate the general trends and really the answer to the question posed in this exercise is that maximum inlet spacing increases as the road cross slope increases. And then if you had a constant road cross slope, whether it's 3%, 4%, whatever, then the maximum inlet spacing also increases as a function of the allowable top width. Now, this particular plot is specific to our data. Remember, we had some 89 millimeters per hour. We had runoff coefficient of 0.9. There was also the Manning's N coefficient for roughness. So this data could actually apply to a specific location on planet Earth. It could be the 300 block of Park Street. This plot could go into a report. So even though we're using this specific data to look at general trends, this specific data also actually corresponds to our specific case for the input data that we provided. One more thing to mention is oftentimes, as far as maintenance goes, and probably some other reasons, the maximum allowable spacing can't be more than a certain amount, say 100 meters or 300 feet. So if that's the case, what would that do to our data? If none of these values could exceed 100 meters, basically I'd rewrite the formula to say the minimum between the existing value and 100 meters. And that's what I've done in this worksheet right here. So we have 100, 100, 100, and we can tell from the plot here that that ceiling for the maximum inlet spacing of 100 meters definitely changes the plot, so that if your road cross slope was 3%, then it doesn't matter if your top width is 2 meters or 3 meters, the maximum allowable spacing will still be capped at 100 meters. It doesn't make sense to have 2 adjacent inlets on a horizontal grade be some 400 or 500 meters apart, even if the hydraulics and the geometry of the roadway say that that is possible. There are sometimes other reasons that you would have a maximum of something like 100 meters of spacing. All right, well, that's it for this exercise. What we talked about was the maximum inlet spacing for a horizontal grade inlet calculator scenario based on the cross slope of the roadway, as well as the allowable top width of drainage.